Hi, today we're going to talk about ordinary differential equations. To be specific, we're only going to talk about first order ordinary differential equations today. So instead of going through any kind of theory, we're just going to jump right into examples and we'll discuss things along the way. So let's start with something simple. We have t squared y prime plus ty equals 2 log of t, and we're given the condition that y of 1 equals e. So that's our full problem that we want to solve for y. So the first thing we want to ask ourselves is, what is the order of this differential equation? So to find the order, we look at all the derivatives in our equation. And what do we see? We see that we have a derivative here, and that's it. I don't see any others. And what kind of derivative is it? It's a first derivative. Therefore, it must be a first order differential equation. We also want to think of who is our independent and who is our dependent variable. Our independent variable is t, and our dependent variable is y. The dependent variable always has the derivatives. So next we think, okay, is this linear or is this non-linear? So how do we do that? Well, in our case, we want to look for any terms that have anything with y, which is the dependent variable, that is not linear. In other words, it's a y squared, or it's a derivative of y squared, or it's a sine of y, or a cosine of y, anything like that. Do we see anything like that here? No. We only have a plain old y prime and a plain old y. No y squareds, no sines of y's, no trig functions with y's in them, nothing. So therefore we know that this here is a first order linear ordinary differential equation. Now that we've classified it, we know how to tackle it. So now we just think, okay, well, how do we solve first order linear equations? And the way we always do that is with integrating factors. But first it needs to be put into standard form. So standard form for a first order linear ODE looks like this. So I'm going to use y and t again just to match our problem here. So it's some derivative of y, a first derivative, plus some function of t times plain y equals some other function of t. So the only spots where we have y are here and here. This is only a function of t, and so is this, only functions of t. So how can we put our equation into this form? Well, looking at ours, it looks like if we divide by t squared, it might fall into this form. So let's do that. We'll divide by t squared everywhere, and we end up with a y prime. Then we have a t divided by t squared. That's just 1 over t, y. This becomes 2 over t squared log of t. Now it's exactly in this standard form. We have a derivative plus some function of only t times y, then some function of only t on the other side. Now we find the integrating factor. The way you always do this is you look at the term that's multiplying y, or whatever your dependent variable is, and we form this e to the integral of that function, in this case 1 over t dt. So what is that going to be? Well, that integral, I think everybody knows, is just log of t. So what is e to the log of t? Well, we know that e and natural logs are inverse functions of each other, and in that case we can just think about them canceling here, and we just end up with this absolute value of t. For our purposes here, we can say that t is positive, and therefore we can drop this absolute value, because remember that the log is not defined for 0 or negative values. So we have to think about that t is only positive here. So this is our integrating factor. It's just t. So here's our equation. What do we do with this t? Well, we multiply everybody by t. So let's try that. T y prime Here the t cancels the 1 over t, and we just get a y equals, now we get a 2 over t log of t. Okay, so now we've done almost all of the work already. What is the point of this integrating factor? Well, we notice right away that if I were to take, say, a derivative of something like ty, right? What would this be? We have to keep in mind that y is a function of t. Therefore, this would be t times the derivative of y plus y, where we took the derivative of t there, and we used the product rule here. And now we notice that this is exactly the same as this. And for integrating factors, this will always be true for linear ODEs, first order. So therefore, this whole thing can be replaced by this. So let's go ahead and do that. So the left-hand side just becomes this total derivative of ty, that's all, equal 2 over t log of t. So now we're almost done. We just integrate both sides with respect to t. Let's do that here. So we're going to have dt dt of ty equals the integral with respect to t, 2 over t log of t. Once we solve these integrals, we're basically done. So let's do it. On the left-hand side, and this will always be true for the first-order linear ODEs, the integral and this derivative will essentially cancel each other, and we just end up with ty. On the right-hand side, what do? We have to solve this integral. Well, the best way to solve it is using a substitution. So let's do it over here. So we have this integral, 2 over t log of t. Let's try substitution of log of t. Then what do? We have du dt is just 1 over t, right? And this can be written also as du is just dt over t. So let's plug this stuff in. So in place of the log of t, we have just u. And then we see here we have a dt divided by t, but that's just du. So we see we have 2 du u. So this is a very simple integral, and we know we can pull the 2 out, and we just get u du, and that's just equal to 2 times u squared over 2. So let's plug back in for u now. We have to remember that u is actually the log of t. So in the end, we have 2 times the log of t squared divided by 2 plus some integrating constant. And we can cancel these 2's. In the end, it's just log of t squared plus this constant. Okay, so now let's not forget what we were actually doing. We're actually just solving this integral, so we'll put that answer back up here, and we have the log of t all squared plus some constant. Now, we're done. All we need to do is solve for y. But that's nice and simple, because all we have to do is divide by t. So y is just equal to 1 over t log of t squared plus c over t, where c is our constant of integration. So that's it. This is our general solution for this problem. But then we have to remember that we were given a condition. The condition was y of 1 equals e. This allows us to find what the c is. So let's rewrite our solution down here. Y equals 1 over t, and I'm going to pull that out. Log of t all squared plus some constant c. And we're told that y of 1 equals e. So what this really says is that when t equals 1, y equals e. So let's plug it in. So y of 1 means 1 over 1, 1 for t, log of 1 for t squared, plus some constant. And we know that this whole thing has to equal e. So what do we have? 1 over 1 is just 1 times, what's the log of 1? It's just 0 plus some constant equals e. And we see here that we're just told that c is e. Now we have our full solution, which is y equals 1 over t times the log of t all squared plus e, because we just found that that constant is actually equal to e. And we're done. And that's our first example. This was a first order linear ordinary differential equation. It will always work the same way. The only thing that can change is that sometimes the integrals can be a little harder. So that's it. Thanks for watching, and come back for our next video where we'll talk about some new equations like homogeneous and exact differential equations.